Hello everyone. Thank you very much for joining our webinar today. The topic for today is Ultrasonic Pulse Velocity Testing for Concrete. My name is Logesh and I'm the Technical and Sales Manager at Proceq. I'm based in the Proceq Asia office in Singapore. And together with me, my colleague, Mr. David Corbett, is joining us from Head Office Switzerland. David is a Proceq Product Manager for Concrete NDT products and also an application expert. For our webinar today, I shall cover the following topics: the UPV basics, the shear wave testing, mainly to measure the E-Modulus, crack depth measurement, and application for about 30 minutes. And later on, my colleague David shall brief us on the Sonic and Rebound method. First, a bit on the history of concrete ultrasonic testing in Proceq. So in the early days, we have the product here called Pico, right? And then in 2009, Proceq acquired Farnell, whom has a world-renowned Pandit instrument. This know-how was added to Proceq's own know-how to develop the most advanced UPV technology in the market. The latest innovation introduces the dry point contact transducers for shear wave testing and also pulse echo testing with tomography, 2D, 3D imaging that we shall cover in our upcoming webinars. As for Pandit itself, the history goes back to 1970s, where sometimes during my visit to testing sites, I still able to see the older Pandit instruments are being used, especially in India, where the Pandit brand name is very popular. Some even think it is an Indian made due to the name Pandit, but actually Pandit stands for Portable Ultrasonic Non-Destructive Indicating Tester. Inspection objectives: where does UPV testing is done and for what purpose? As-built verification, meaning that UPV testing is used to test new structures to check if they conform to the specifications. Integrity assessment: UPV is used to test the structural integrity of existing structures. This can be for renovation, routine maintenance, or preparation for building extension. Materials characteristics: UPV testing is also widely used in geology, primarily for E-Modulus testing to characterize the rock type or strength. So here are some of the information that we can obtain from UPV testing. For example, the uniformity of concrete, cavities, cracks, thickness, the E-Modulus, concrete strength, and so on. How does a UPV instrument work? There's some animation here. So you can see there is a concrete segment here with a known length, D, right? So you place a transducer, the transmitter, and the receiver face to face, and we send a pulse from the transmitter, right? Send a pulse, right? And the instrument will measure the time taken from the transmitter to the receiver. So you see, the instrument just measures the time, right? And then we already measured the length, so the distance and time, we can calculate the velocity in meter per second, right? Now, how does the velocity useful to us, right? So there are several guidelines or national standards available where we can classify the concrete quality based on the pulse velocity. For example, a concrete velocity above 3,500 or 4,000 can be deemed as a good quality. Below 2,500, we can say is a poor quality concrete. Let's look at this example here, right? I would say that UPV gives us a qualitative statement. Why, right? So imagine this column here, right? And we are measuring a few locations A, B, C, and D, right? So the point A is a good quality concrete, so we get high velocity above 4,000 meters per second. But at point B, C, and D, due to the defects, right, you can see there's a drop in the velocity, right? Now, when you pass this information to your customers or client, right, they might ask you, can you tell me why at point B, C, and D, the velocity drops? The answer is no, you can't tell. You can just say the velocity drop, but why? Is it because of void? Is it because of crack? Is it because of honeycomb? We were not able to do so because, as I mentioned earlier on, the instrument just measures the time, velocity, that's about it, right? So you want to do a more detailed investigation, you have to go for advanced techniques, right? For example, like a pulse echo, when you can do some imaging, right? Now, let's look at point number C, for example, right? So we mentioned here, if there's a void, you can expect a large drop in the UPV. So one example here, right? So we made a block here in our office. So the path length is about 0.6 meter. And we place a hollow PVC pipe, right, at about 50 mm diameter. So this is the size of a tennis ball, right? And I'm going to do a measurement on this block at two locations. The first point, I'm going to do a measurement at the bottom here. Done, right? Now my second point, I'm going to measure directly across the pipe, right? A huge hollow pipe, right? Done. And one more measurement near the top, right? So we had a measurement at 3 points. So we see how's the point number 1, point number 2, number 3. So point number 2 is where we have the hollow PVC pipe. So you can see here, the value, right, as compared to the good area is very small drop, right? Only 70 meters per second. So if you don't know, right, there's a void here, you will say that, okay, at this particular point, I'm getting above 4,230 meters per second. So we can say it's a very good quality. And look at the size of this pipe, it's a 50 mm, so it can be neat, you see. So that's why I say that normally for UPV, right, it's very good for us to get a qualitative statement or uniformity or general quality, right, of the concrete. So normally, like a lot of testing companies, what they do is that they measure the column and they look for the uniformity. Let's say the reading is more than 5% difference, then they will do more thorough investigation. So it's very good for us to get a first-hand information. That's what UPV does, right? So are we saying that UPV is not useful at all for detecting defects in concrete? Well, it can be, right? It can be, provided the defects are large enough, right, that cover the whole area of a testing where a significant drop in pulse velocity can be measurement arrangements. Whenever possible, right, direct transmission is the best since we have a defined path length that gives the most accurate UPV measurement. In case we are measuring on floors on a long wall where direct measurement is not possible, then we can opt for semi-direct or indirect measurement. But as indicated in the standards, when you do a measurement, semi-direct or indirect measurement, there will be a drop in the pulse velocity as compared to direct transmission. So you can see here a single kind of block with the 0.6 meter length, right? So I'm using a exponential transducer here so that I can get a more accurate pulse length. So you can see here, when I do a measurement, direct measurement, I get about 4,084 meters per second. Now the same block, I do a semi-direct, now I'm getting 3,681 meters per second. So that's about 10% drop on the velocity as compared to direct measurement on the same kind of, exactly the same concrete, right? If I go to indirect, it drops further to 3,384 meters per second. So another 20% drop as compared to direct measurement, right? So this kind of point, you have to take notice. So whenever possible, do direct measurement. If not, maybe semi-direct or indirect, you have to cater for the, or mitigate for the drop in the velocity. And also, if you look at the waveform here, right, the waveform here as compared to the direct, indirect, and semi-direct, you can see that the waveform here, the amplitude is much more higher, meaning that the signal strength received is much more stronger. Now, let's look a little in details of the ultrasonic wave type, right? So normally for UPV testing, we use the P wave, right? And also we have another component called the S wave or shear wave and the surface wave for the radial wave, right? So I can show you a simulation here, right? How does this wave propagate in a homogeneous material, for example, a metal, for example, right? So you can see the wave will travel through this material, right, and bounce back. And just observe the waveform, the A scan here, right? So I'll start the video now. So you can see the P wave travels, here, in the receiver, the first A scan. And the wave comes back, goes back again, the second time receives, then second echo, and followed by the third time, the third echo, right? So you can see here, I can see the first echo, second, and third one, right? I play one more time. Now you see, you have the P wave coming first, and the S wave, and the surface wave here, right? So this is a simulation done on a wave propagation of homogeneous material. What about a simulation on inhomogeneous material? For example, like a 32 mm aggregate concrete, right? So again, just observe, right? So now you can see the signal is more grainy, right? Scattering, because the concrete is more attenuative, so it's even a signal, right? It's a bit noisy, the second echo, and by the time the third echo, it dies off, right? So there is a significant, right, a scattering of the signal, more noise and more difficult to interpret. So in concrete, the ultrasound is that we need more analysis, right, to get a good signal, right? In this slide, it shows how the P wave, right, propagates through a concrete where the particle displacement or direction is parallel to the direction of wave propagation. That's for P wave, right? Or they call it compression wave or longitudinal wave, right? Whereas in shear wave or S wave, the particle displacement or direction is perpendicular to the direction of the wave propagation. So that's the difference between P and S, right? And P wave, normally, it travels faster than the S wave. So you can see here the P wave and S wave. So the P wave will travel first and followed by the S wave, right? So the pulse velocity of the S wave is lower than the P wave by about 55 to 60% and also has a smaller wavelength, right? So sometimes in some application, right, the S wave can be useful because of the following reasons. For example, better signal to noise ratio, less attenuative than P wave, and also in dry point contact transducers, the amount of S wave propagated in concrete much more than the P wave. So you get more signals and very good power, helpful for our analysis. Now, what can influence our UPV testing, right? Size and geometry of concrete does not influence pulse velocity, but the density and E-modulus does. So you can see the relationship between velocity, the density, and the E-modulus. So E-modulus and the density affect our UPV reading. Rebars are major factors, right? So sometimes conjectured rebars can increase the pulse velocity in concrete, right? When measurement done, especially when rebars are running in parallel. So the velocity of a steel is about 5,900 meters per second. So if you see your EPV measurement coming close to this value, you can suspect probably the pulse is actually running through the steel rather than the concrete. Moisture has a large effect on concrete, especially during the curing stage. Temperature has an effect, but not in the range of 10 degrees Celsius to 30 degrees Celsius. Out of this, right, out of this temperature, there is a correction factor given the standards that you can use for your correction of the UPV value. So that's some of the influences you can expect when doing the UPV measurement. Now, transducer selection. There are many types of transducers available with different frequencies. So which one is good for you, right? Again, I would say you can refer to this standard EN 12504 that gives a recommendation for transducer. To summarize, basically what they're saying is that for shorter path length, you can use a higher frequency, right? For longer path length, you can use a lower frequency. For example, you are measuring more than 3 meters or 5 meters, you can use a lower frequency transducer, for example, 24 kilohertz transducer, for example. As for Proceq, by standard, we provide a 54 kilohertz transducer, which satisfies most of the applications. Okay, so that's the basics. So next, we move to the shear wave testing. Most of the time, shear wave UPV to measure the resistance of deformation from loading for concrete and also for classification of rocks, for example. So in UPV, we measure the dynamic E-modulus. But for concrete, normally the static E-modulus is required, but this is a time-consuming lab test. So the UPV dynamic E-modulus can be correlated to static E-modulus, right? So there is a empirical relationship between the dynamic, right, and the static E-modulus given by the formula here. So this is given by, and also if some of you interested to do rock testing, the UPV, I would recommend this standard ASTM standard D2845. If you have a chance, please get hold of this standard. It's a very good paper to explain regarding how to go about doing the rock testing with the UPV. Now, let's see how we can do the shear wave testing with Proceq transducer. So this is our Proceq dry point transducer, right, dry point transducer, and no coupler is required. So screen measurements, no stain from the coupler, and it has an automatic trigger, so one person can operate the instrument. So for E-modulus measurement, right, So the instrument, from the instrument, we need to get the P wave and the S wave. And after that, we need to input, the user has to input the density of the material they want to measure. For example, concrete, the density can be about 2,000 plus kilograms per meter cubic, right? So once you enter that, and when the instrument measures the P wave and the S wave, the E-modulus can be measured automatically. So I prepared a video here, right? So you can see here first, this block here is about 0.6 meter length. And first, I fix with the P wave transducer. This is a 54 kHz transducer, and I will start my measurement, right? So you can see here, the measurement is started. So first, the first cursor here, right? So this is my P wave, right? So now I'm using a P wave transducer. I move the cursor manually to find the zero crossing here. After that, I continue the measurement, right? So now I need to do my S wave testing. So I need to change my transducer now to the shear wave transducer, right? And I'm doing the measurement at the same point again. So now I do the measurement of the S wave. So you can see my S wave will start to come. So it's a bit more weaker. So I will increase my gain here a little bit, yes. And now I move my cursor right to the zero crossing and stop the measurement. So that's all. So my measurement is done, right? So I already entered the density of the concrete earlier on. That is about 2,200 kilogram cubic. And the path length 0.6. And I've already measurement. The first one, I find the gray color waveform. I try to find zero crossing on the P wave, right? After that, I change to S wave transducer. Then I measure the I move the cursor to zero crossing of shear wave, and automatically the instrument, right, will measure for me the E-modulus. So you can see the measurement is very, very fast. Within 5 minutes, you can complete the measurement. But maybe more time is needed for you to prepare the sample. For example, rock, for example, you have to core it, you have to polish it, right? So that's the sample preparation will take more time, but the measurement itself is very easy, automated. So that's for the shear wave testing. Next, we move on to the how can we do the crack depth measurement with the UPV, right? Okay, so before we go about doing the test, right, we have to ask ourselves some questions first, right? How to determine the orientation of the crack? Does the crack travel straight down, or does the crack slope to one side? If yes, to which side? Is it going to the right or is it going to the left, right? And how can we ensure our results are as accurate as possible? Okay, so in our finding instrument, we measure the depth of crack by time of flight measurement, right? First, we place the transducer at position B apart, right? Then we measure the time, right? And thereafter, we move the transducer at position 2B and measurement of the time again. And with the T1 and T2, by using this formula, the instrument will automatically measure for us the crack depth or the height of the crack, right? So it's very easy as well. So first, you place the transducer, position the transducer at position B, measure time, and then move to position 2B, measure time, and by this formula, we can estimate the crack depth, right? Now, understanding crack, right? There's a few points I want to highlight when you want to measure the crack depth, right? So crack depth are not typically uniform throughout the length of the crack. So example, this is the surface of the concrete. So your crack won't be, right? It won't be at the same depth. It can be shallow at some place, it can be deeper at some place, right? So in that case, you have to take multiple measurements, right? Take multiple measurements along the crack, right? So that you can get an average value, for example, right? So here, there's a crack here, right? You can see the person has taken measurement 1 point, 2 point, and 3 point, and this is the measurement that obtained, right? And always, right, report your data in a minimum, maximum, and average depth of crack, for example. So one measurement is not enough. You take multiple measurements and provide all these, all the data collected. Now, sometimes when you do the measurement, there could be some foreign particles, maybe some stone or sand inside the crack. So what happens is that, for example, here you see a crack here, but there's a stone here. So what happens is that instead of the pulse travel all the way to the end of the crack and come to the receiving transducer, you will take a shortcut, right? You pass through the stone, for example. So in that case, again, you can get some error in your measurement. So please take note of this as well. Okay, so all of us know that concrete is good in compression, but weak in tension, right? So that's why you put rebars in the concrete. So let's look at here, right? So you can see a crack on the surface. When I core out, you can see the crack goes down, But once at the rebar, it stops, right? So once you hit the rebar, it stops. So crack stops there, right? So what I'm trying to say is that before you do the measurement of crack, please map out the position of the rebar. So you can see here that the rebar running behind, but you're doing the measurement right on top of the rebar. So what happens? The pulse instead of traveling to the concrete or below the crack, you might pass through the rebars, right? So again, you can get some error in your measurement. So before you do the measurement, please check the rebar location, map out the rate. And also, there's a crack here. The person doing the measurement, but you can see here, this measurement, there's another crack here, multiple cracks. So doing measurement, multiple cracks also can give you a error. So please take note of this as well, right? Okay, so final part, application. I'm going to show you some details about application or some pictures where the UPV used. First of all, correlation to comparative strength. So sometimes you have seen that a lot of customers or clients, they use a rebound hammer for correlation of strength. UPV can be useful as well. So later on in a while, my colleague will talk more about this on the combining the UPV and rebound method for SONREB, right? Some additional information I want to pass to you is that, what the UPV measure is just bonding, right? Bonding between the cement, the stone, the sand, and that's about it. It's not a direct measurement of strength, right? So there could be a lot of possibility, a grade 20, grade 30, grade 40 cube, right? Have the same UPV value, right? It's possible. And also nowadays, in the concrete, they put a lot of additives to increase the strength, right? So one of the our customers has feedback to us saying that, when this kind of concrete, when you have additive, they can see a difference of UPV when you, at for example, a strength of 30, 40, 50 MPa. But above that, when you go to 55, 60, 70, right, the strength is increasing, but the UPV will remain the same. It's saturate, right? So these are some of the points you have to take note, right, when you're doing correlation of UPV to the comparative strength. Strength development during the curing stage. So you can see here, there is a particle instrument being used for data logging to monitor the curing efficiency at start and after 3 hours and after 6 hours. So you can do a data logging to check the curing efficiency, right? Application, conflict quality and uniformity testing. So you can see a lot of UPV testing being done to check the structural integrity, uniformity on a column, on a beam, on a water tank here, right? So a lot of measurement being done. On a metal structure, so these are features given to us by our customers taken some years back. I think they're using the older version, the TICO, right? So this is a metal segment being in Thailand, Bangkok, right? This is a measurement on the structure. And also a precast element, also for metal segment, this is in India. So all these precast structures are 100% checked. So they're using a 24 kilohertz transducer here because the length is about 3 meters, right? So very useful, and they do a lot of measurement to check the integrity of this structure on this precast element. On knee-built structures, so you can see the stain of the coupling. So some of customers, the testing companies, the informers, over the weekend, they can take thousands of measurements, right? So it's very useful tool. UPV is a very useful tool for us to get a first level investigation, right, of the concrete quality of the integral structure, right? Very useful tool. And a power plant, power plant chimneys, again, right, can be used to check UPV can use to check the structure integrity, power plant and so on, right? Okay. So with that note, I come to my end of my presentation. So finally, I just want to show to you the Proceq Pandit family. We offer a wide range of ultrasonic testing instruments, UPV, pulse echo, imaging, and so on, together with a variety of transducers, accessories that to complement this measurement, right? So that's all for myself. I shall pass it on to my colleague David to take over to brief us on the SONREB method. Hi, David. Yes.
Okay. So, SONREB, as Logesh mentioned, people use ultrasonic pulse velocity also for strength testing. In Europe, we have the EN 13791 standard for compressive strength testing on site. And it basically has exactly the same standard for two test methods. One's the rebound hammer, and the other is ultrasonic pulse velocity testing. That's ultrasonic pulse velocity testing alone. It's the first time we've just revised this standard actually, and it actually mentions now that you can get useful information by doing the SONREB method. In China, they have a national standard for the SONREB method, and in some other countries also, Italy and Europe were the first to do a lot of research on this, and they have a national test for this. So what is SONREB? It basically comes from two parts. The SON is sonic part, which is ultrasonic pulse velocity, and the REB is for rebound hammer. So that's where the name comes from. And why is it? Why do people do this test? You have a compressive strength formula. It's based on this type of formula. V here is the pulse velocity. S is the rebound hammer value. That comes from the Italian word sclerometro, which is a rebound hammer in Italian. That's why it's written as an S there. But that's they did say in Europe they were the first to really do a lot of testing with this method. The reason why people do this, if I have, this is an example test data. This was done in the UK. You can see all of these samples. Each one of these was a block, and we get a correlation factor between pulse velocity and compressive strength. You can see the correlation factor is 0.71. Testing on exactly the same blocks with a rebound hammer, we get these results, and you can see we have a correlation factor 0.78. And if we combine the two in a SONREB test, we have this correlation factor here of 0.85, so much better correlation. And if you look on the internet, you'll find many studies on SONREB that people have done over the years, and generally you get better results by combining the two tests. Of course, it's more work, but you get better results, and that's why people do it. How to do this? It's actually, if you want to generate this SONREB curve in Excel, it's quite complicated. You can see on the left-hand side here, I have the compressive strength results from core testing. I have the pulse velocity measurements and the rebound hammer value measurements. I have to take natural logs of all these values and then do this. It's an array function called linest in Excel. So you can see it's actually quite a complicated method. But to make things easy for our customers, we created an Excel macro to do this for you, which is this determination of SONREB coefficients. So you can download that from the Proceq website. And it looks like this. So you just enter your values in the table here. You press Control Q, and basically it generates these constants A, B, and C. And we can enter these constants then. Last input from my side on strength testing, where Logesh mentioned before, this EN12504-4. That's actually the standard for pulse velocity testing, European standard. That's currently under revision. It was due to be released this year. It's difficult to know actually right now with the current situation with the coronavirus, how that's going ahead, but we had a review meeting in January. Up until now, it's only been possible to use P waves to measure pulse velocity according to the standard. And in Europe now, we're changing that also to be able to use shear waves, which actually should speed things up generally. You know, the big problem you have when you measure with P waves is mapping out the grid on both sides of the structure and then coordinating people to do the measurement. And in future, once it's allowed in the standard, we should just be able to do it with a pulse echo measurement. And basically, there were no objections to this. I mean, Logesh showed you the test before, the comparison, doing direct measurement and indirect and semi-direct measurements. By far, the most accurate results are with the direct measurement, but the standard actually allows all three. And with the pulse echo method, you also measure through the whole structure. So the accuracy is comparable more with the direct measurement. And this was actually the reason why it's going to be allowed in the standard in future.